Memory. After this section, we'll have gone through memory, functions, lifetimes, that's a weird concept, lifetimes, pointers, and arrays. The first thing I'd like to go over is how memory is structured. Where is everything in the computer? If my computer is running my program, there's a few things it obviously, well, I think fairly obviously, needs to know. It needs to know what my program is, what the instructions are, so it needs to find those somewhere. It also needs to know the variables that I'm talking about, things I'm storing values into, the things that I'm taking values out of, adding together, putting back. And there's a few places that those can live. In memory, we basically say memory is just this one long row of cells. Each cell has its own address. The first one is cell 0. We usually write these in hexadecimal, so that would be 00000000. The one after that is, unsurprisingly, cell 1, 2, 3, and it goes all the way up to the end. And the last one is 0xFF. The largest number I can express using 8 hexadecimal digits. That's not important, though. The point is, each cell has an address. They go in order. Everything in the computer's memory lives somewhere in one of these cells. So everything has an address. You can, for an example, find the address of a function and find out where the code for a function lives. You can find the address of any variable in your program. You can find the address of the arrays. So, up near the start, up near that 0x00, if we go down a bit, we're going to find our code. Code lives up this end of memory, and then after that, we have some extra stuff followed by the heap. We'll get into the heap a bit later. But the important stuff for now is the stack, and that's if we keep going all the way down to the other end of memory, we find this thing called the stack. Note that is different to a stack, which is a data structure. They work kind of similarly, but the stack is more important. And the stack sort of grows backwards, back towards us. Every time we call a function, the variables for that function are pushed on that end of the stack, and it comes back towards us. We say the stack grows when we call functions. So each instance of a function, I say instance because when I call a function, what I really do is I find out where the instructions for that function are, and I say, I know this function is going to need like variable A, variable B, variable C. Those variables don't live with the code for that function. They live on the stack in what's called a stack frame. So I say I'm going to run through the instructions for this function, and the variables for the function are going to live all the way down here. But I can call this function multiple times inside of itself. So because the variables live in a stack frame, I might actually have 1, 2, 3 different stack frames which are all using code from the same function. The most obvious way this tends to happen is when we have a function that calls itself. Did you have a question? No? We have a function that calls... Can I draw a diagram? Let's see what amazing technology I can use today. I will use pen and paper. I do not have the advanced technology that Andrew does. What? The whiteboard's not going to be... I don't think. Pen and paper is fine. Please tell me this is visible. Ooh, that's a weird color, but sure. Let's go with it. So, we have our memory here. Excuse my handwriting. Up here we have 0x0000 ... Down here we have 0xFF. Is that too many F's? That's not enough F's. So, memory looks like this. At the top we have the zeros, down the bottom we have the F's. there's a section just around here which contains our code. And just under that, we have the heap. Down here we have the stack, which grows in that direction. Right? If we take a closer look at the stack, so say we have our stack down here, and this is our main function. So this contains all of the variables that are living inside of our main function, and it's right at the bottom of the stack. It's not actually true, there's stuff underneath it, but you don't need to worry about that. If I have a function that was called, say, let's go back to the code. We look at the first function that calls is getHidden. So the first thing that'll do is that'll set aside a stack frame for getHidden. And inside of that stack frame we had a single variable that was hidden. So this is all inside here, right? So hidden gets put on top of main. This is the stack frame for getHidden. We put the variables inside of that. When the function returns, this stack frame disappears. It gets popped off the top. None of the variables that were in that stack frame exist anymore. Instead, what happens is, in place of that, we then have our stack frame for check guess. Check guess. And inside of that we have, I really wish I could erase this, but sadly I can't. We have the guess, we have correct, because that has two variables. And that lives inside of the stack frame of check guess. So whenever we call check guess, that puts a stack frame on top of main. We put the variables in there that we're working on, read in stuff from the user, put them inside that stack frame, figure out whether or not they were correct. If they were correct, we send back that whether or not they were correct into main. That gets copied back into main stack frame. And then we destroy that thing. And we keep doing that, creating one, figuring out if they were correct, getting rid of it, until either we run out of guesses or they guess correctly. So there are a few key points to be made about stack frames. So each instance of a function, if I call a function multiple times, it gets its own stack frame. They're pushed onto the stack and they get popped off and destroyed when a function ends. The question is, yes?
So only one function within main is stored in memory, right?
Huh?
Can only one function called within main is stored in memory at a time?
So if we assume your computer is only doing one thing at a time, then yes. But that function might call other functions. If that function calls other functions, the stack frames for those get put on top of that, and they just stack on top of each other. But yes, at any given time, there will only either main will be running, or we'll have one function sitting on top of main that's running, or one function on top of that. Does that answer your question? Fantastic. Fantastic. So, question is, how do values end up inside of these functions? Well, if we set aside some space in these functions, we have these variables. Either we create the values inside of the function and store them there then, but we could also copy the values into the function stack frame when we create the function, and we call these arguments. So arguments are just variables, but when the function is created, we copy some values in. And then the function may also copy one value back out of its stack frame into whatever called it, into the thing below it on the stack when it returns. So we always copy some value in and copy it out, copy one out at the end, or we create the values inside, which leads to some issues, because it's fine if I just have some numbers, I pass some numbers in, and that function gets its own copy. But if I have, say, some struct that represents student, and that student has a name, they have an address, they have a height, and they have a mark, my function is going to give them an HD. And I try and pass that struct in. What actually ends up happening if I don't do anything more than just passing it as an argument is that struct gets copied into that function stack frame. There are now two of these students that exist in the world. There's the one inside the function that had the stack frame, and there's one inside the function I've just created, the one I've just called. So this copy gets given the HD. But this copy also disappears when the function returns, unless we copy it back out as a return value. So we create this copy of this student. There's two that exist, one inside the outside function, one inside the inside function. We give the one inside an HD, and then it disappears. We say the one inside has the lifetime of the function that it was copied into. It doesn't exist beyond that. That's what we mean by lifetimes. It's how long does this value stick around. And it doesn't always make a lot of sense to be copying things around. It doesn't make a lot of sense to have multiple copies of many things. So we use pointers. Because if I can only copy values into functions, instead of maybe copying the value itself, I find the address, the number of that cell that that value lives at, and I copy that address into that function. So that function, instead of having its own copy of this student that we're giving an HD to, it knows where that one student lives, and it can go and find it using its address. That's all that pointers are for, so that we can have that one copy of that thing that everyone is referring to using its address. I had some other notes on pointers. Doop, 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 doop. This is all going wonderfully. Pointers, pointers. Yes, so pointers let us do what we sometimes refer to as pass by reference. I give you a reference to where this thing lives rather than giving you your own copy. So you have any questions at this point about variables and functions, arguments, return values, or pointers? Any questions whatsoever? Because I know pointers can get a bit tricky. Using pointers is hard. But that's all that pointers are. How about I write some code? Quickly. So I have, let's say, some struct student. What did I say the student had? Say the student had a name, 80 characters long. They have an age. They have a height. I don't know why I need to know that height, but I guess it's just there. And they have a mark. So now what I want is, if I say, have this function which int main. So I create this student. Let's say Jashank. You're a student, right?
Yes.
Shank name equals Jashank. It's not going to let me do that, is it? Let's use a fun trick here. Can't do that, but I can do this, for the sake of brevity. Dot Jashank, dot name equals Jashank. Age equals, let's just make something up. Height In centimeters or feet? Let's say it's centimeters. Let's say 165.2. And the mark, Jashank's current mark, is 65. Not doing so well. Oh well. So this creates our student. So what this does is this actually creates the struct and it sets all of the initial values. This is something you are actually able to do. Let's say I have a function that is void give HD. And it takes a student. It's really bucketing out there, isn't it? I'm glad I'm in here at the moment. How many marks is an HD? Let's say s dot mark equals HD. So I have this function and it gives the student an HD. So I say hash include stdio.h print f the student %s as the mark %d, except s dot mark. What's this? Oh, it wants me to give the student name as well. Okay, now it's happy. What I'll do is I'll actually do the same outside. So if I say give HD Jashank. Clang. Ignore that. If I say, so if I run this program, Jashank has the mark 85. Actually, let's make this a bit clearer. So when I run this, it says, give HD says Jashank now has an HD, he has a mark of 85. But main still thinks that Jashank has a mark of 65, which, it's good. It's a credit, isn't it? It's a credit, good effort, but we wanted to give him an 85. We wanted to give him a high distinction. So the reason why this has happened is when I passed the student struct, Jashank, into this function got its own copy, and it gave that copy 85. So instead, what we want to do, is there a question there? Is there a question? No? What we want to do is give a reference. And now this is going to yell at us because I can't use dots. There's a whole bunch of things it's complaining at me about. So, because I now have a reference to this struct, I need to dereference the pointer in order to change the value. So the normal way I dereference pointers is I say star. But that's kind of awkward, because what if this struct itself had a pointer in it, and then that was pointing to a struct that had a pointer in it, and that was pointing to a... That gets messy. So instead we have this nice bit of syntactic sugar, we like to say, which is this arrow or this stab. We use that to dereference the pointer to a struct, and then look at some value, change some value. And if I'm going to pass a value into a function that's expecting a pointer, rather than expecting the value itself, I have to say where that thing lives. And so I give it the address of that thing. Give HD, we gave Jashank a mark of 85. Main agrees that he has 85. Keep in mind that everything we've been using up until this point is on the stack. We have not touched the heap yet. Often when we're dealing with, whenever we're dealing with the heap, we have to use pointers. Because the variables aren't stored in the stack, we can't use just a name to access them locally. We have some pointer in the stack that tells us where in the heap the thing is. But at the moment, everything is in the stack. Everything's right at the other end. And we're just pointing in between things in different functions. So if I were to go back to the document camera, this would be like, I have my main. It has this thing called Jashank. It's got a name, it's got age, he's got height, he's got a mark. And then we call this function on top of it called givehd. And that has this s, which points back down into main and tells us where that struct is. Any questions at this point? All keeping along? Keeping up? All right. So, back to the internal computer, display on both projectors, pointers, arrays. If I look back at my notes. So, yes. Type def? Yes, but not right now. We'll do that a bit later. The list of things I have to go over a bit later are type def. There was another one you asked about. It was, you remember what it was? Sorry, what? Scanning in multiple numbers. Scanf and type def. Scanf and type def. Don't let me forget. Arrays. Arrays are like normal values, except everything is stored next to each other. So if I have an array of integers, it's just a bunch of integers next to each other. And if I'm referring to the array, I'm usually referring to the address of this one at the start. So this could be numbers. And there's a few different ways this looks in code. Now, my array doesn't have to be of numbers. I could have an array of structs. I could have an array of students. In fact, let's take a look at what that might look like. So much switching between inputs. So instead of just having one student, I could in fact say struct students. A student, students. Let's say that there's 5 of them equals. So if I had an array of ints, I could say int numbers 5 equals 1, 2, 3, 4, 5. Right? That would give me an array of numbers. It would give me an array of 5 numbers. If I take away the size there, I'd still get an array of 5 numbers. Just because when I'm declaring an array, when I'm creating an array to begin with, this says, figure out how big you are on your own, based on how large this thing is over here. So I could make an array of 5 numbers, an array of 6 numbers, an array of 7 numbers. I could also say, make sure you have 100 numbers in use. This is 100 integers stuck next to each other. The first one would be 1, the second would be 2, the third would be 3, the fourth would be 4, the fifth would be 5, the sixth would be 6, the seventh would be 7, and every other number would be 0. Likewise, if I do this, the first number would be 0, and every other number would be 0. If I do this, suddenly I have no idea what any of those values are going to be. They could be whatever. Seems silly that if I don't tell it anything, it isn't just all automatically 0. Wasn't my decision. That's just how C is defined. It's weird. Anyway, I can do the same thing with structs. I could have an array of structs. So I could say, give me an array of 5 students. And because I can define structs like this, this gives me an array students, the first of which is Jashank. And then the rest are all 0, I guess. Then we have Dean, age is 10, height is 120.2. Mark is 72. Almost a distinction, not quite. And then we say, that's it. So we have 2 students in this array of students. So this array is the actual structs stuck next to each other with their values inside them all next to each other. And instead of giving an HD to just one of them, I want to change this function so it gives an HD to all of them. And so I give maybe a pointer to students. Does that make sense? This seems to be happy if I just say students. So when I say that when we're referring to an array, we're usually referring to the address of the first element. What I mean is, we effectively just have a pointer to the first thing. So this still makes sense. This doesn't. While int I equals 0, while I less than 5. Student I. Oh, this is getting long. Break it over multiple lines. Oops. Print out all the students. Strangely, there's nothing complaining at me about this being wrong. What do you think will happen if I just run this program as is? I've got 5 students, and I've said give HD to students. So I assume it would give an HD to all of them, right? Let's find out. Oh dear, what did I forget? I++. Easy mistake to make. Even the best of us make it. Try again. So you can see there are 5 students, the last 3 don't exist. Jashank was given a mark of 85, but Dean still only a credit. So, to make it a bit clearer that this is actually working on a function, on an array, we'll write it like that. But that still means the same thing. It's just trying to make it clearer that we're passing in an array. We'll do the same up here. If I go down here, give HD, it knows where the first element is. How would this function find out how many elements are in this array? What can it do to figure out how long this array is? Anyone have any ideas on how long how we would figure out how long the array is? If I wanted to give everyone in the array an HD. How would I figure out when I've reached the end of this array? Anyone got any ideas? You might think that I might be able to say something like, while students I not equal to 0. That sometimes works, but this is complaining at us, because that's expecting S. Now it's complaining at us because it's comparing an integer with a thing. How would this function possibly figure out how long this array is? If all we have is the start of the array, we don't actually know how long the array is. There's no way for us to figure that out. The only way this function can know how long this array is if it gets told how long it is. Five students. Once again, I've got the all-important I++. So easy to forget. It's still a pointer, we're still passing it around just like a pointer. Any questions at this point about arrays and functions with pointers? If we pass a value into a function and we get a pointer, there's actually no way we can tell the difference between a pointer to one value and a pointer to an array of values. They look the same. Generally, if we're passing an array into a function like that, we also pass in a variable that tells it how long that array is. So we need to know the length. That's usually what tells us the difference between those two things. Do you guys have any questions about arrays at all at this point that I can answer for you? Yes? EOF. So EOF is a special value, and what it means is that I've reached the end of a file. If I look back at my code, which is somewhere here, that one. What about this would be the end of a file? I have an array of things. It's not really a file, so EOF doesn't really make sense here. EOF is useful in helping us to find the end of a file, but not really useful in helping us find the end of an array. We will see soon when EOF is useful. Any other questions about arrays? Or anything that I've spoken about up until this point? Six, 4, that'll do. We can use loops and arrays, passing arrays into functions. How would I pass an array out of a function? If I made an array in a function, like, let's say I want to make a function that creates a list of students. It would have to return the pointer to the array, I guess, because that's how we refer to arrays. So it would look something like struct student create student. Oh. Let's just say void for now. Figuring out how long it is going to be hard. So we want to clean up our code. We want to make these students in this function. Move that down here. Stick it inside a function. Just return students. Because I'm taking a pointer, I say students equals, there is something it's not happy about down there. Make sure we have a prototype. Can we just do that? Could I just create the array in this function and hand it back? Hand back the reference to the first element in the array. Who thinks I would be able to do that? Who thinks this would be a great way of creating arrays in functions and handing them back? Who thinks there might be some reason why I can't do this? Yeah, this array lives inside of that function's stack frame, which we mentioned earlier. Once this function returns, everything that was in there disappears. So if I tell you where this was living when it was in the function, then the function returns, you find out where it was, and then it sort of gets a bit messy. Specifically, this says, address of stack memory associated with local variable students is returned. It's saying we're trying to give back an address to something that won't exist once the function ends. It's trying to be helpful. Let's ignore it and run it anyway. What do we think might happen here when I try and run this? Any guesses? So I don't have DCC, so I don't have all of this useful stuff that you're used to tell me when I've made a mistake. I'm using Clang, which is like DCC, but stupid. It trusts that I know what I'm doing. Do I know what I'm doing? Probably not. But it'll let me do it anyway. So when I hit enter, it's gone a bit funny. Dean, I think you failed the course. So it's not as if the data was destroyed. We passed an address of an array that was inside of a function back. Most of it still seems to be there. The information hasn't moved. But some of it's been messed up a bit. And that's because when I call a function again, so I call this first giveHD. First I call create students. That makes the array. Puts the array in memory, writes it into the stack, puts all the students in, and then returns. And then I call giveHD. Where does the stack frame for giveHD go? It goes on top of main, and that's where the stack frame for create students was. So it goes on top of where that array was being stored, and it puts its own crap there. It just spits stuff all over it. And so we get random bits of other information stuck in random places, and Dean horribly fails the course. GiveHD thought we gave Dean an 85, but by the time we got back to the main function, Dean had quite badly failed the course. It's an impressive mark. Although whoever came after him did quite well. So, if I wanted to create a function that generated this list of students, what might I have to do? Where could I... Surely this must be possible, right? Being able to create an array of things and pass it back. How would I do it? Clearly I can't put the memory in the stack frame. Is there somewhere else I could put the memory and then refer to it?
Well, speaking that arrays are already pointers, couldn't you pass the array into a function and quantify it there?
Yeah, but I don't really want to do that. I don't want to have this whole array in main. I just want it to be somewhere else. I want it to create it somewhere else. But yes, I certainly could do that. I could have this empty array. I could pass it into this function and then pass it back out. But I sort of want this function to create the array out of nothing. I don't want to have to sort of feed it in stuff to sort of help it along. It should be able to be just fine on its own. Where could I find somewhere to put this array so that when this function returns, it doesn't just get written all over? The heap. That's ingenious. Why would the heap work? The heap works because, well, that's what the heap is for. Pretty much. Huh? Gives us memory. We say, oh, all right, I want to reserve enough memory for 5 students up in the heap, all next to each other. I'm going to put my array there, and then I'm going to pass a reference to this back. when this function disappears, it takes all its variables away with it, but this stuff is still sticking around in the heap. So if I give you a reference to where the array was in the heap, it'll still be there when the function returns. How would I request from the computer some memory in the heap to store an array? What can I use to do that? Sorry? Malloc. Malloc's not all that intelligent. So it needs a bit of helping. But I can still say student, struct student. Malloc is going to give us a pointer. But Malloc needs some help. What information does Malloc need to work? Malloc needs to know how much memory we need. So I need 5 students, and to say that I would like 5 times however much space it takes to store a student. And then what I will do is I will say, because I want 5 of them, what was I going to do next? Int I equals 0 while I is less than 5 I plus plus. I can say students I equals students I dot name 0 equals. So because the array has already been created, I can't just sort of copy a string in there. Well, what I could do is I could say make this the empty string, which is the same as saying make the first character of this string equal to 0. How are we doing for time? In a word, poorly. I could say students I dot age equals 0. Student I dot height equals 0.0. Student I dot mark equals 0. So I set up this struct. Why is this? Oh. Then down here I have to change this a bit. Why is that happy? I'm suspicious of this. Did I not? Oh. If I'm going to use malloc, I have to say stud lib.h, don't I? And I need to be passing it into a pointer? Did I not do that? I did not do that. Yes. I can't just say make this array now equal to this string. What I have to do is I have to copy it. Copy. Let's just use function for this. Copy. Oh, hey, these should all be semicolons as well. Wrong? And the wrong way around? Dest string. Damn it. This is why these functions are painful, because apparently I got that the wrong way around. Oh. To make what I
actually succeed in doing so, of course, but
Okay, that seemed happy. Now if I run it again, after many attempts, it seems to work again. Everyone gets 85s. That took some time. So, we can use malloc to get some memory in the heap. We can store single values in there. We can store arrays in there. And have references to it a little later on. Now I have to look at what my other notes were. Size of... Right. One problem with the heap. Once we're done with something that we've allocated in the heap, we need to say we're finished with it. If we don't, it'll stick around for a while, and that may not be a problem in a program that's small and is only 10 lines long, but if you're writing a complex piece of code like a web server or a web browser, or most software is now web servers and web browsers, isn't it? It's pretty much all software at this point. Or a database. One. But if you're writing this big complex piece of software that needs to run forever, and you keep getting things in the heap and then just sort of ignoring them and forgetting about them, then you'll run out of memory because this thing that you're no longer using anymore is stuck around and it's taking up space and you don't need it anymore. So what you need to do every time you make a malloc, when you're finished using it, when you're no longer going to need it, when you're no longer going to refer to it, you must free. So we know that create students uses malloc to get some memory. We use free to then free it up. There are some more complex ways of using free that we'll see later. How am I doing for time? Okay, that was the end of the notes I had. It's terrifying. What came after memory? Then we go strings, right? Strings. It's easy to confuse strings with arrays. Strings are not arrays. Strings are things that live inside of arrays. String is a sequence of characters that ends in a null. In this case, we mean like the 0 character value. Now, when we store a string inside of an array, whether that's in the heap, whether that's on the stack, the string has to be shorter than the size of that array to fit it in plus the null. But because I know whenever I am passed a string in a function as an argument, that it will be less than the size of the array and that it ends in a null, I don't need to know how long that array is. I just need to find that null that marks the end of the string. However, you shouldn't be confused with any other kind of array. Strings are a special value that we store in arrays, and we can only use that null when we're dealing with strings in arrays. No other sort of array generally makes sense to search for a special value to find the end of it. You always need to keep track of where how large the array is. Questions about... I'm going to take another short break for a couple of minutes, and then we're going to start talking about reading, writing from files, I/O, scanf, user input. Stand up, stretch your legs for about 2 minutes. We'll move on to that. Can I get everyone to sit down? We're going to blitz through the last few parts of this lecture. We're going to talk a bit about reading and writing very quickly. There are 3 key things we need to consider. Hash include. There are 3 things we generally care about with input and output. Reading input from user, sending output back to the user. Second one is easy because it can all be done with printf. Printf is your friend. Except when implementing it, yes. I can printf strings using %s. Text. Wow. I can also learn how to spell eventually. This is the bane of all of my demonstrations, is my inability to spell. I'm going to cheat here and I'm going to say this is on the stack. Key thing to note here is this string here. If I did this first one, this is an array of characters. It lives on the stack. I can go and do something like text for, let's say, 7 equals n. I can go and change it. I can change the values inside of it. Yep. It'll look weird, but it'll be fine. Yeah, that's right. I'm writing single characters, aren't I?
What's the difference then between double quote and single quote, Herbert?
That's an excellent question, Joshane. Double quote is a string. It represents a bunch of characters stored in order and ending with a null. This, in double quotes, is a string. Characters are numbers. They're the bits that make up the string. So we use single quotes to represent just one character. What does it not like about this? Incompatible. Why were you fine with the other ones but not that one? Because you're fine. What I can't do is this. This string is, we get a pointer to the text. This is on the stack. However, it's not on the stack. It lives up with the code. And we can't change the value of that in most cases. In most cases, the compiler won't let us do that. So I couldn't say text2 7 equals O. If I try and compile that, I get a segmentation fault because of it. Not very useful. Anyway, I can print strings. This isn't the stack because I can change it. I can also print strings to file. If I wanted to open a file that I'm going to write to, I can say file star f equals open fopen io.txt, and I want to write append to it. Let's say append. The difference between W and A adds on to the end, W goes to the start, and R lets me read from the file from the start rather than writing it. And so I can change these to fprintf, does the same thing, but it ends up in F, in the file. So if I call this and I run it, and then I cat io.txt, you can see that it's all ended up in there. If I run it again and I cat it again, we get 2 copies of it. fprintf and printf also let me do numbers.
Excuse me.
Yes?
Sorry, can you explain more slowly, please, what the code is doing?
Yes. My only problem is that we have to have lunch in about 1 minute. So what I might do actually is I'll end it here and I'll pick